Okay, so what I want to talk about in this lesson is the idea of how particle size of the reactants can impact on the rate of a chemical reaction. So if you remember, when we're talking about the rate of a chemical reaction, basically what we're talking about is a change, like how quickly the concentration of the products or the reactants change over a period of time. Um, so if we think about a chemical reaction, for example, what we have here is we have this substance called it's marble or calcium carbonate. So this here, so we've calcium carbonate, and we have the difference in the two is the particle size. So we can see here in this top one, the particle sizes are quite big, so we have big chunky pieces of particles. And whereas if we look at the bottom picture, the calcium carbonate is ground up into fine powder. So this is calcium carbonate. So, and its chemical formula is CaCO3. So you have a calcium atom bonded to a carbon atom, and it's bonded to three oxygen atoms. And this is known as calcium carbonate. Carbonate. So this part here, the CO3, is where the carbonate comes from. The calcium comes from this first part here. So if you take calcium carbonate and you react that with hydrochloric acid, so hydrochloric acid is the acid that's in your stomach and it's used to digest your food. So it's a fairly strong acid. So you've the hydrogen bonded to a chlorine atom. And this 2 in front indicates that there's 2 moles of this. So if you have 1 mole of calcium carbonate and you react it with 2 moles of hydrochloric acid, we'll just write this in here. What's going to happen is this will react with each other and it'll produce 3 products. It'll produce calcium chlorate, so chloride, should I say, CaCl2, plus water, H2O, plus carbon dioxide, CO2. So you have calcium chloride, water, and then you have carbon dioxide. So carbon dioxide is the stuff that we breathe out. We all know what water is, and then you have calcium chloride. So this is, so if we remember then, so the on the left we have the reactants. So these two here are the reactants, and they react each other to give us the products. So this is a change over time. So imagine we have, so imagine just, and I'll represent, so we've hydrochloric acid, okay, particles like this, okay, or the molecules if you like. So imagine they're represented by green here. Now, if we think about what has to happen for a chemical reaction to take place, there has to be contact between, in this case, the calcium carbonate and the hydrochloric acid. So imagine we put these in contact with each other. So this is a solid and the hydrochloric acid is a liquid form, okay? What's going to happen is, in order for these to react with each other, so these have to come into contact with each other. They physically have to come into contact with each other in order for a reaction to happen and take place. So when we have, let's say, big chunks like this, all that can happen is the rate of reaction is going to be slower, because what's going to happen is the hydrochloric acid can only really react with the calcium carbonate particles that are on the surface here like this. So if you can imagine, let's say within the body of this, there's going to be calcium carbonate, but it's shielded or protected from coming into contact with the hydrochloric acid because you have because it's inside within the particles. So the bigger the particles, the less surface area, if you like. So if you think about all this surface area here, so when you have big particles, you have less surface area for in this case for the hydrochloric acid to come in contact with. Now, and in order for the reaction to happen, there has to be contact between these two reactants, between the calcium carbonate and between the hydrochloric acid. So the bigger the particles, so the bigger the size of the particles, the less of the surface, the less surface area available. And if there's less surface area available, the slower the reaction will take place. Okay, so the bigger the particle size of your reactants, for example, the less surface area that's available. The less surface area that's available, the less contact that you're going to get between the product and the reactants with each other. And what will happen is it'll have a slow rate of reaction. It'll actually slow down the reaction. Now, on the other hand, if we think about something like this, so imagine if we have a powder and we take this powder and we dump it into some hydrochloric acid. We dump this in here. What's going to happen is it's going to disperse and spread out, and you're going to get much more contact between the hydrochloric acid particles and the calcium carbonate particles. So they're going to come into contact with each other, and what's going to happen is you're going to get a much faster rate of reaction. Why will you have a much faster rate of reaction? Because with smaller particles like this, when they're ground up, you have a bigger surface area. There's a bigger surface area in relation to the surface of your calcium carbonate has increased. So there's much more of calcium carbonate that is in contact with hydrochloric acid when it's ground up like this. When it's in lumps like this, you have calcium carbonate that's going to be inside in the middle of the lumps, and that won't be able to react with the hydrochloric acid until the outside calcium carbonate is moved out of the way so that this can come in contact. So what will happen is that will slow down the rate of reaction. Whereas when it's ground up like this, and this is put into the hydrochloric acid liquid, for example, it's going to spread out, and you're going to get much more contact between these two guys. And when there's contact, there's going to be reactions. When there's reactions, it's going to happen faster, so it is once there's more contact. So that's really like fundamentally the size of your particle, the size of your particles of your reactants, for example, if one of them is in solid form, which in this case calcium carbonate is, the bigger the particle size, the less surface area that's available. The less surface area that's available, the slower the reaction will take place. So imagine, whereas if you ground down your reactants, in this case calcium carbonate, you're going to have much more surface area. So if you think about when this is spread out, there's much more, the hydrochloric acid is going to be in contact with more of the calcium carbonate. And it's really as simple as that. The rate of reaction is impacted by the size of the particle. Increase the particle, you reduce the rate of the reaction. So when we say the rate of reaction, it's how fast these products are changed, these reactants on the left hand side are changed into products on the right hand side. So if you were to time this, so you were to time it, let's say, so the quicker this happens, the faster the reaction is. The longer it takes for this to happen, for reactant changing the product, the slower the rate of the reaction is. Now, what you can actually do then in relation to this is you can set up an experiment that's something like this, and this can be done in the lab, and it just demonstrates this idea of particle size and how it impacts on the rate of the reaction. So again, it's the same reaction. So we have calcium carbonate, we react with hydrochloric acid, and it gives us calcium chloride, water, and carbon dioxide. So this is going to be a solid. Okay, so solid. This is going to be a liquid. This will be solid. this will be a liquid, and then this is going to be a gas. So this is going to be a gas, and this will be dissolved, let's say, within the liquid. So what we have here, if we have a look at the apparatus, so we have a balance. So this is our balance here. We have a graduated cylinder. We have a conical flask. Inside it, we have the marble chips, which is this here, the calcium carbonate. So we see here we have it in solid lumps. We have then the hydrochloric acid, which is the liquid in here. We have a timer then as well. So the idea is what you do is you take all of your apparatus like so. So you measure out an amount of hydrochloric acid. You measure out, so you're going to change the size of the calcium carbonate particles or that you start off with. So we start off with a particular size, and then what you can do is you can like reduce the size, to carry out the same experiment, reduce the size and see how that impacts on the rate of the reaction. So what you're going to essentially get then, so this is your setup. So you have the solid, so solid, liquid, and gas. So, and what you have here as well is you have cotton wool to prevent the spray escaping as well. So basically what's going to happen is you will set up the apparatus like this, put in your marble chips or your calcium carbonate, measure out an amount of hydrochloric acid, put the whole lot on a balance and take the weight, like so. And you'll record this weight. Then what will happen is you will mix, you'll put this inside, you'll take out this cotton wool, put in your hydrochloric acid in here, and then what will happen is these will come into contact with each other. So essentially what you're doing is you're adding these two products together, and then you put the whole lot back on the balance and you set your stopwatch. And what's going to happen is over different periods of time, you're going to measure the change in this mass. So what's going to happen is the reaction will take place. So the calcium carbonate will react with the hydrochloric acid. It'll produce the products. So you'll get calcium chloride, you'll get water, and then you'll get carbon dioxide. And the carbon dioxide is going to, it's a gas. So what will happen is the carbon dioxide will come off and it'll be able to pass through this cotton wool. So it's going to pass off here and it's going to pass off into the environment around the apparatus. So what's going to happen is we're going to lose mass. So the drop in mass, so this number here is going to drop as the time goes on. This number will keep dropping down, so it will. And the reason you're losing mass is because this carbon dioxide is being produced and it's being lost out of the apparatus through the cotton wool. The whole idea of having this in here is that we don't want like spray, or we don't want to spill or lose any of the liquid, because if we do, we're going to lose some of this and some of this, and then our measurements will be inaccurate. So basically what's going to happen is you mix these two together, and then over time you set your timer and you watch as this number drops, and it'll keep dropping until it gets to a point where it won't drop anymore. And once it stops falling, the mass stops dropping, that means that this reaction has completed and you're not going to get any more reactant being produced. Now what we can do is we can take this information and we can put it onto a graph. So what you have here is you have your x-axis, so we have the x-axis on both here, and then you have your y-axis. And what's going to happen is over time, so if we think about this, in this one, what we're looking at is the loss in mass in grams. So what you're doing is, as the mass reduces, you're taking the new mass, you're subtracting it from this, and then you're plotting it as your y coordinate, and you keep plotting it like this. Now what you're going to do is you're going to run this experiment a couple of times, and you're going to use different sizes of, so you start off with this size, let's say, of calcium carbonate, and then you might use a slightly smaller, you might crush it up and make it slightly smaller for the second run, and then you'll do a third run where it's even smaller, the particles of calcium carbonate, the product that you're starting off with is even smaller. So then what you do is you plot these against each other. So you run your experiment and you plot the difference, and what you'll get is you'll get a graph that looks something like these two here. So what you can see is that you can see, like with the small marble chips, so when the particles of the calcium carbonate are really small, the rate of reaction is very, very high. So what's happening is the change that's happening, if you look at here, like, so this is, let's say, high, and this is low, and this is low, and this is high. So what we have here is that we have a high loss in mass over a very short period of time when the particles are small. So you can see here, like, it takes this length of time for the reaction to take place when the marble chips are small. If we look at, in contrast to that, let's say when the marble size is medium size, so it takes from about here for the reaction to complete and take place. So you're talking about this period of time. So it's a much bigger period of time. And then if we look at the final one, then let's say when you have large marble chips, you can see here that it takes roughly up around here. So it takes this amount of time from here to here for the reaction to take place, which is even a bigger amount of time. So we can clearly see here that this is the fastest. So the reaction rate is fastest when the marble chips are small, whereas this is the slowest when the marble chips are bigger, and it's for the reasons that I've talked about. So this again is a way that we can demonstrate and show experimentally the impact of the size of particles on the rate of reaction. So what we have here in this graph, we have time. Okay, so time is coming from our stopwatch, and then you have the total mass in grams. So what's happening is you're starting off up here. So it's all starting off up here with this measurement. And then as time goes by, the measurement starts to drop. So this mass starts to drop because you have your calcium carbonate coming off here. And what's going to happen is it's going to produce this type of graph as well, which is, it's almost the inverse of this one up here. So again, you get the same thing. You can see the same thing. The biggest loss in mass happens over the shortest period of time when when you start off with small marble chips, or when this calcium carbonate, when you grind it up and it's small, whereas the slowest is when you start off with big lumps of calcium carbonate. So that's just that's basically, you know, how when we think of particle size, how particle size impacts on the rate of a chemical reaction. So thank you for listening.